Okay, I think we are living in really exciting times today because, as you see, I mean, these methods like deep learning are tremendously powerful, and we will see some examples in a moment. Also, they influence and currently infuse various areas of mathematics, like inverse problems, also partial differential equations. But on the other hand, if you look closely at those applications, you see that there is actually almost no fundamental mathematical understanding. And so from my perspective as a mathematician, this is still a huge problem. So we have all these powerful methods, and also people are starting to use them now for very sensitive applications. Still, I mean, the deep understanding is lacking. And so what I will talk about today is what is already there in the theory, maybe also which questions we actually have to ask from the area of mathematics. And then tomorrow, we will talk about inverse problems, because there, if you go to conferences, so one of my areas is inverse problems, and this is also how I came to deep learning. Now, if you go to conferences in inverse problems, at least 80% of the talks already use methods from machine learning, in particular from deep learning. And so then tomorrow I will also talk about how deep learning methods, so first of all, what are inverse problems, what has been done traditionally, and then also how deep learning methods are now used in this area, also maybe combining them in some sense with traditional methods. And this is also what this basic theme of the spring school is, which I think is very important in some sense, how, let's say, the connection between models and data can be in the most beneficial way. Good, yeah, so the impact of deep learning, as I said, I think a lot of people, I mean, all of you know that deep learning has a huge impact. I mean, just think of self-driving cars, where these methods are now used to make decisions, whether to drive left and right, whether to evade a pedestrian, and so on. I mean, then certainly also surveillance tasks, for instance, face recognition. I think a major area where deep learning methods are used is healthcare. So this appears in various instances. For instance, as already said before, in inverse problems, magnetic resonance imaging, computed tomography, where for the reconstruction people use now deep learning methods, either pure deep learning methods or combining them with traditional methods like sparse regularization, but also not only for that, for solving the inverse problem, but also for suggesting decisions to the physicians. And maybe also in the end, in the future, to reaching really critical decisions like whether to continue life-sustaining measures for a patient. Then the other area are maybe what I might call legal issues, and so I showed this slide also at Caltech, and so there I was notified that in fact in the US, in many instances, job applications are already evaluated by deep neural networks. So this is already there. It will certainly be more in the future. And so I think this shows also how critical this is, and also how critical it is that we as mathematicians, in some sense, enter this area and then also provide a deep understanding for that. And so I think it goes even further. A lot of people are talking whether deep learning is actually artificial intelligence or what it has to do. So what I found fascinating, I'm sure maybe some of you are aware of this, so there was this AlphaGo. So Go is a game which is much more complicated and complex than chess. And so it was a long time not possible for computer algorithms to actually beat the top world players, which come from South Korea. Now with AlphaGo, which is actually based on deep neural networks, it was possible to beat the top world players, but now there is AlphaGo 0. And AlphaGo 0 is, I think, quite amazing. So AlphaGo was trained on all, let's say, different moves of players in many games, but AlphaGo 0 trained itself. So it started with nothing but a blank board and the rules of the game. It learned simply by playing millions of games against itself. So then you can ask and debate whether this is already artificial intelligence or not. I mean, there are various ways, but this is not the main point of this lecture. Yeah, but I think it shows that there is a lot of potential, and people also have deep belief in these methods. Then when it comes a bit closer to mathematics. So for instance, in imaging science is also one area I work in. What was, I think, quite fascinating and maybe also quite shocking. There are algorithms, for instance, for denoising, where people worked on for tens of years, designing deep learning, designing denoising algorithms with a lot of theoretical understanding. And deep learning methods suddenly came out and with quite ease, actually maybe not completely beat the state of the art immediately, but which came very close to it. So then also PDE solvers, I mean, there it's not that evolved. One can debate how useful it is in that area, but also, for instance, solving the electronic Schrödinger equation. So by my colleague Klaus Robert Müller from TU Berlin and his team, I mean, they have, I think, very interesting work in now solving this equation in, well, milliseconds, basically. And then in this whole area of inverse problems, as I already said, so inverse problems, you have a forward operator which you want to invert. So for instance, the forward operator puts noise on the image and you would like to invert it, or the forward operator takes parts out of the image and you want to invert it, or here, which is computed tomography, there these deep learning methods show, I mean, tremendous success. And so this will be also part of what I will talk about tomorrow, because with these traditional methods like sparse regularization, you reach a boundary which people worked on it for tens of years, cannot get beyond. And so now, using these deep learning methods, you can actually reach, I think, quite spectacular results. But as I said, I mean, for me as a mathematician, I found actually this article very nice. It's from Siam News. It's from my colleague Michael Latt from the Technion. And he called it Deep, Deep Trouble, Deep Learning's Impact on Image Processing, Mathematics, and Humanity. And so this article talks about that there are now these really powerful methods which often almost beat the state of the art, where we have all the theoretical guarantees, but these methods now come without any theoretical guarantees, so we don't have any fundamental understanding. So, and this poses a significant problem. So you can ask yourself, what do you do in a situation like this? Do you just keep going with, let's say, methods like sparse regularization and so on, where you have a deep fundamental understanding, or do you embrace these new methods, but forget maybe about everything you believe in as a mathematician? Or whether you go the route and aim to look at these methods and aim to develop some theoretical foundation for them and use them maybe also in the best possible way in combination with previous methods. And so these previous methods usually also have some physics in them. So using deep learning, and this is what you see, I think, also a lot these days, is that it is so easy. You have your neural network, you have your inverse problem, you're just training on a lot of data, and if you forget everything what you know about physics, and then the deep neural network will do so and so. I mean, it will produce kind of good results. But what I think in a lot of these applications is forgotten is that, I mean, we know a lot about the physics, in that sense, about the models. And so the question is, how can we actually bring this in and maybe combine this knowledge in the best possible way with these new methods like machine learning and deep learning? And so this is what this article, I mean, it's just 2 pages. So if you're interested, you can just read it very quickly. But I think this is also the core question for everyone who is doing research in maybe not all areas of mathematics, but I mean in many areas of mathematics, what to do in the situation of this type. Good. So a need for theory. Yeah, I think there's a whole need for theory. And what I would like to do in the beginning is to discuss with you what questions we actually need to solve. Yeah, so what are the core questions we need to attack? And then we will look at each of those questions. And for each of those questions, we will discuss what is already there. Certainly not all results, but I will give you some samples of those results which are already there. And then what still needs to be done. Good, so let's maybe start and discuss where this all came from. So the first appearance, I mean, neural networks are not new. So they were already there in 1943. And McCullough and Pitts, they had the idea to develop an algorithmic approach to learning, and what they wanted to do is to mimic the functionality of the brain. And so their goal was to design systems which mimic or which produce artificial intelligence. And so they were very hopeful at that time, so they mimic the brain. You will see later on how, let's say, the functionality of the brain is actually encoded in a neural network. Then one can debate whether this is actually enough, whether there's more from neurophysiology, how one can build these networks off. But this was the idea at that time. Good, so let's look at the first definition of a neural network. We will have to be a bit more precise later on, but let's first see what neural networks in mathematical terms are. And I mean, Ron already gave, I think, a very nice introduction in his talk, so let's look at it also from the point of view which notation we use here. So you usually see these pictures. So what do they mean in mathematical terms? So in mathematical terms, one can view a neural network as a function which has a, let's say, a highly structured function in this way. So you have these W's, which are affine linear maps. And in between, you have these sigmas, which are called rectifier or also activation function. These are typically nonlinear functions, and they are univariate functions. So here they are then applied component-wise. Yeah, so let's just look at this example here. So you have a four-dimensional input here, x1, x2, x3, x4. Then these connections encode the first matrix. We will see that in a moment a bit more closely. So this function goes from R4 to R5. Then in here you add these what's called offsets, and also in each of these neurons you then apply these rectifiers. And there are also a lot of possibilities. And then you keep going. So you can view this. As I said, we need to be a bit more specific later on, but in general terms, this is what a neural network does. And certainly later on, you will learn these affine linear maps. Yeah, so let's look a bit closer at what these connections mimic. Maybe you're already aware of this. So here, for instance, we have something in R3. This is our matrix. So then, I mean, these connections just mimic that the first output is a combination of the first two of x1 and x2 with those weights. The second is this weight times x3, and then here, third. And then in here, you apply these offsets, you apply the activation functions, and then you keep going. So for instance, then you have a map to R2, and these connections, as we discussed before, mimic this matrix. Now, what one is interested in also is to have a network with very few connections. Why? Because you are interested to have a network which is very efficient, which you can maybe also store in an efficient way. And so you see here clearly what it means that you don't have that many connections. It relates to the fact that these matrices have a lot of zero entries. Yeah? So these are sparse matrices. If these are sparse matrices, you get a network which is sparsely connected, which is very few non-zero entries. Okay, so this is clear, I guess. So, yeah, so if you have any questions, just also interrupt me and ask in between. Good, so how do you train these networks? Or what do you do with these networks at all? Typically, you have a function, a complicated function in the background. Usually, it's assumed that it lies on some lower dimensional manifold, like, for instance, you see here. And maybe you would like to learn a function which gives you a classification. So which classifies certain areas of the manifold as 1, 2, 3, and so on up to k. So for instance, think of this situation. You have this manifold. On one area, you have images of images of dogs. In the other area, you have images of cats. And now this function kind of cuts this manifold in half. And so on one area, you have cats. The other area, you have dogs. And so what you're given are sample values of this manifold and function values. And so what you now do with this neural network is you have to decide a lot of things. The input dimension is typically clear. L. I think I didn't say this too clearly, so let me see. Yeah, so L is always the number of layers. So this is the number of how often this is concatenated. N will be the overall number of neurons, so which is the sum of all those dimensions. And so D is the dimension of the input layer. Okay, so D is usually clear because you know how large your images are. This is your input. But then you need to decide how many layers you actually take for your network. You have to decide for each layer how many neurons you actually have. And you have to decide which activation function to choose. Typically, one chooses the same activation function in the whole network for each of these connections. Sometimes you're even a bit more specific. You might want a network which is not what's called fully connected, which means that, as I said here, you have the number of layers. You know how many neurons there are in each layer. And so if you just choose this, then, I mean, we would start with a network where you have all different connections here. Sometimes you don't want that. For instance, in inverse problems, people typically take what's called a U-net because it looks like a U. And so this you encode now already before in these matrices. Because if you now already in the beginning say, I don't want all connections here, just very few, then you put already a lot of zeros of these matrices equal to 0. Now, if you have this, then the next is to learn these affine linear functions. So what you want to learn are these matrices, and you would like to learn these biases. And typically, you do this by solving an optimization problem. So let's take a closer look at that. So this is your network function. Evaluated in these points xi, where you have sample values. You would like this to be close to f of xi. The closeness you measure by some loss function. So this could be the square loss, for instance, so the square difference. And then you might want, for instance, that you have a sparse network in the end. So you also put an additional what's called regularizer on the weights and the biases. So maybe the L1 norm or something like this with a regularization parameter. And then you would like to minimize this functional. And so once you do that, we'll also go a bit more into the details there. Then eventually you learn all these matrices and biases, so these weights and biases. This gives you this function. Or this network, so you know now the weights and the biases of it, and then you hope in the end that what you get out, so this phi, this is the same phi as we have here. So this phi, you hope, is close to your initial f. Yeah.
Well, in your example, you say f takes only finitely many values. Are you thinking of classification?
Yes. Yeah. That's right. So this is just an example.
So it's not exactly true, because I mean, phi takes the way you define phi takes it's a continuous function taking infinitely many values. So it's not going to be that phi is exactly equal to f, but maybe that the risk function, I don't know, you're going to do something.
Sure. So this is just in a way for forgetting the intuition.
Okay, so you.
Yeah, but I mean, so the manifold could also be a compact manifold, so you can. Yeah.
But it could be regression. You're estimating your own function.
That's right. It's just an example. Yeah. So this function could look also very differently.
Okay.
It's just forgetting the intuition. I think the main point here, because what we want to evolve now is see what you actually, where you want to build your theory on. Is you have your sample values, you select the architecture, then you learn these weights and the biases, hoping that in the end the network recovers the function, the complicated function in the background. So this is in a way what a neural network does. Good, so then there was a second appearance of neural networks, for instance by Jan LeCun and his collaborators. And what is the reason? The main reason why neural networks became that popular again are two. One reason is that now we have a lot of computational power. And so we can train networks with hundreds of layers. And this, for instance, also raises the question, why is depth that important? And this was already mentioned by Ron. Also before, we could only train shallow networks, so with just very few layers. Now, these deep neural networks seem to have a tremendous advantage. Also, we have a lot of training data available, which was also not available before. So for instance, if you want to train your network on images, you just go on the internet, you can download billions of images, and you can train your neural network on that. So these are the two factors. And what I said before is, the current situation, also to my mind, and you will see on the next page that I'm not the only one thinking that setting up a neural network, deciding upon the number of layers, upon the number of neurons, and so on, is more or less trial and error, and based on a lot of experience. The training itself is quite unpredictable. And there's almost, if you have a neural network, no understanding why and how it reaches decisions. And so as I said, I'm not the only one thinking that. Maybe you saw this article. You don't need to read everything. So there was an incident, Ali Rahimi. He's a researcher in artificial intelligence at Google. He received a prize. And in his speech, as it says, he took a swipe at his field. But interestingly enough, he also received a 40-second ovation for it. So he said, for instance, machine learning algorithms in which computers learn through trial and error have become a form of alchemy. So they tune their learning rates without understanding why one algorithm is better than the other. AI researchers training their algorithms are, which is maybe a bit harsh, stumbling in the dark. And the process still relies on trial and error. And then one can think, these algorithms are very powerful. Do we trust them? But my standpoint here is, it needs a lot of mathematics. Good. And so these are, for me, some of, the most fundamental questions which we need to ask. The first is this area of expressivity, and there Ron already said a few words about that. So there we can ask, we have an architecture. How powerful is it? Is it powerful enough to at least is able to approximate the function which I want to learn? So this will not always be the case. Can it represent the correct functions? So this area uses a lot of approximation theory, applied harmonic analysis. These are the main tools for solving those questions. The second is the learning itself. So it's usually learned by stochastic gradient descent. You will see also later on how this algorithm works. But it's not clear at all why those algorithms actually learn something reasonable. So in the end, you have a lot of, it might end up in a local minima, but it's not clear which local minima is good for generalization and so on. And also what are good starting values for this algorithm. So there, goes a lot of, say, differential geometry, optimal control, optimization. So these are areas from mathematics which do and will contribute, I guess, significantly to that question. Then the area of generalization, which is, I think, the most difficult and least understand. And you will see, in a moment also what, in a bit more depth, what generalization means. It basically means we have these sample values. But what I want is that my algorithm not only performs well on the sampling values, which I know, but also on other values, which come maybe from the same distribution. Or if you go back, so here I want that my phi actually not only approximates these values, but in fact the whole function f. Good, and also, for instance, here what impact has the depth of a network, and so on. So there are, learning theory, optimization, statistics, I guess will be the main tools. But in general, there's not that much, I think, very convincing work yet done. And then the last area, which I personally also find quite, quite interesting, is this area of what people now call explainability or interpretability. So that asks the following question. I have my trained neural network, And now I want to understand how it actually reaches decisions. So what I might want to have is, let's say I have I have my image, and usually people take images of cats or dogs, so I have my image of a cat. And I want to know which pixels contributed most to the decision. So I have the decision that this is, so here I have my neural network. And then I have the decision that it's a cat, let's say. And so what I would like to do is I would like to go back through the network and put, for instance, a heat map on this image so that I know maybe these pixels are, let's say, the most relevant for reaching that decision. So if I would change them, maybe the decision changes the most. In the end, I guess what one might want to have is, let's say you applied for a position somewhere, and then you get a rejection, and you would like to know why you are rejected. But the decision was done by a neural network, so you might want to know, as I said, which features of your CV maybe contributed most to the decision. And so then in the end, you would like that this area is able to explain the decision of the neural network indistinguishable from an explanation of a human being. So this would be maybe the vision. But then the question is, how do humans reach decisions? Or how would an explanation of a human be? In any case, so this is what this is about, in a way, understanding, if you have a trained neural network, how decisions come about. Also, for instance, if you use it for inverse problems, there what you might want to know is how certain the network is in the output image about, let's say, the reconstruction. So this will be important also for physicians. So if you have, let's say, in the end, an MRI image, the physician would like to know how certain the network is. If there's an area with a tumor, whether this network just invented that or whether it's really something which is in the input data. And so here, information theory, maybe uncertainty quantification, these areas are the most important, which contribute to that. Okay. Good. So what I would like to do now first is just very briefly tell you about mathematical learning theory, because this is, I think, also the basis for everything to some extent, and also it will show you where these networks came from, and also it will also give a different, it will show you again that these expressivity, learning, and generalization are in fact the key questions. Then we will go through these 4 points, so expressivity, learning, generalization, explainability. That will be today, and then tomorrow we will talk about applications of deep learning to inverse problems. Okay. No? Everyone agrees? Happy? Okay. Good. So let's talk a bit about learning theory. Not too deep. I just want to give you the flavor of it. We don't want to go too much into the details there. So we will first look at it from a very basic level. Then we will see the general theory, the continuous theory. But as I said, it's just to deliver the main concepts. Okay, maybe the most basic is a definition by Mitchell, who said a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P, if its performance at task T as measured by P improves with experience. So all these elements you find in these deep learning algorithms. So the tasks could be, for instance, classification tasks. So very popular in deep learning are these handwritten digits, which you would like to classify. So there you have an image, an n by n image, and then you would like to output the value of that digit. Or it could be a regression task. You would like to learn a function of this type with real output values. So like Albert just suggested, for instance, prediction of future of prices of securities. Or density estimation could be where you have a probability distribution which you want to learn, maybe to detect some corruption in your data. Now, so these are tasks which you might want to learn. The experience is typically given by these sample values. So this is what you have at hand. So that's these xi's or xi, yi, and one in general distinguishes two different types, supervised and unsupervised learning. So the supervised learning is where each data point is associated with a label. So for instance, images of cats have the label cat, images of dogs, the label dog. Unsupervised learning, there the data points are not labeled. So you just have a bunch of pictures and you would like to, for instance, cluster those. The performance measure is typically, and also with neural networks, what's called cross-validation. So we separate our data set into two parts, into a training data set and a test data set. The training data set we use for training the neural network, as we saw before, and then we hope that it performs well also on the second data set, on the test data set. Yeah, so this is our performance measure. This is how we train it. And certainly in the training phase, the network or however learning algorithm you choose should absolutely not see the test set. Otherwise, I mean, everything is in vain. Good. So these are, in a way, the ingredients, typical rough ingredients of learning. Let's just look at one example, and then we look at the general theory, but then I think it comes out very naturally. So let's say I want to predict a function, a regression function. I have my data. I split it into a training and test data set. This is my performance measure. So what I would like is that the test data set, that's how I measure my performance, this function which I estimated performs well, and so what I do here is I take the square loss. So these are the three ingredients. So now how do I do that? First of all, certainly it's very difficult to take all different functions f, so I restrict my set. I have usually additional knowledge about them. Maybe it's a continuous function, maybe I know something else. So what I now assume is that I have a hypothesis space where my function, which I want to learn, lives in. Later on, in neural networks, this hypothesis space will be the functions given by neural networks. So here, very easy, I take my hypothesis space, just a span of these finitely many functions. Okay, it's just an example. Then I have my training data. Yeah, so these points xi and yi. And I train it in the following way. So this is what I know. I would like that on the training data, it performs well. So I look at this difference. I look at the square difference. And this I want to minimize. Very canonical. So what's called then the empirical target function. So this is the empirical error. Empirical target function is then the minimum over that. And so here it depends on the hypothesis space. So I restricted my set of functions I look into, and I look only at the training data. Good. So then, I mean, this is actually not difficult to solve, because what can I do now? Every function f, I can write as a linear combination of those. Yeah, so every f I can write in this way. I have my training data. I have the w, and if you go back, you see here I now have the sum over those applied to these points. So what becomes important are these phi i's applied to these xi train. And this I put in a matrix. And then if I write everything, I just get this function to minimize that we can easily do. So I get a minimizer. And then this is in the end my estimator. Okay, so this was just an easy example showing you all the components which are there in a learning problem. And so one can now look at it in a much more general setting. So the general learning problem looks as follows. There are different ways to write this. So this is one. So I have a probability space. I have two random variables. vectors in Rn, Rk, k equal to 1 would be the regression. And then I'm looking for a function which, given a value in here, predicts the value y in y. So I want to learn this function. And the measure, the error I want to measure by some loss function. This could be the square loss. And so the error which I define is this error which you see here. So f of x should be close to y. I measure the closeness by this loss function, and then I take the expected value. And so then the learning problem is learning this g. And so now, I mean, from now on, we just restrict to k equal to 1 and to the square loss. Okay, so that's the learning problem. And now we see all the ingredients from what we saw before popping up again. So first of all, what we observe is that there is always one function, one element, which is a minimizer, which we can just write down. This is the so-called regression function. I don't want to go too much into the details there. So it's also a function from x to y. We can explicitly write it down. That's the main point. And I can write my empirical, my error function in this way, which shows that if I choose this regression function, this is actually a minimizer. So anyhow, so the main point here is there exists a minimizer. Then what I do next is what we also did before. We restrict our space. We cannot minimize over the whole space, so we restrict it maybe to a subset of the continuous functions, could be also something else. Then we are looking at a function in this space, so we minimize just over the space, as we did in the easy example before. Still, I mean, this cannot be solved, since we don't know this distribution rho, which is in the back. But at least we made it already a bit easier by restricting to this hypothesis space. Now there are a lot of choices for hypothesis space, polynomials, reproducing kernel Hilbert spaces, and so on. Good. So the next thing we need to do, as before, is so what you see here is that it is actually quite crucial how to choose your hypothesis space. Yeah, so let's see. I choose my hypothesis space only linear, affine linear functions. So then if these are my points, if I choose only affine linear functions, I get a very bad approximation. If I choose maybe quadratic polynomials, it becomes a bit better, and so on. But you see here, if you choose, let's say, maybe two high degree polynomials, you start what's called overfitting the data. Yeah, so here you do underfitting, here you do overfitting. And so this overfitting is also dangerous because maybe you also have some outliers which you now take into account, although you don't want that. And also you might fit it too closely so that then if you have other points, it doesn't generalize that well. And so this is also when you hear in deep learning, overfitting, underfitting, whether it's not clear because you have so many different parameters in a deep net, why it does not overfit. And so this is also behind this in a sense. Good, so the next thing is we restrict now to sample values. We don't have this distribution, but we have sample values available. Sorry, this needs to be capital N. And so what we can look at is now this error, not the other which we had before. So now we look at this error, the loss, maybe the square loss of f of xi and yi. And now we minimize this. So now we made these two reductions. We looked at the hypothesis space and the sample values. And so this is in a way the core. What you see is that this error which you make consists of two parts. It has the sample error and it has the approximation error. So I mean, this equation is very trivial. You see, I mean, you just add and subtract this E of fh. But this is a sample error which is also depending on the hypothesis space. This is the approximation error which you make by choosing your hypothesis space. And so this is what's called sometimes Bias-Variance Tradeoff. So if you choose your hypothesis space too large, or very large, then the approximation error certainly decreases because you approximate by many more functions. But the sample error will increase. Because then, I mean, if your hypothesis space is very large, you just have the same number of samples, certainly that error will get worse. The smaller you choose H, the sample error will decrease, but the approximation error increases. So that's good. And so now, coming to the end here, we see now that the errors which we discussed before, we can observe here. So initially, we want to solve this very general statistical learning problem. Now, for instance, the regression function is one example. Then we actually said, okay, I cannot choose this in its full generality, so I choose a hypothesis space and choose it in that space. So here I make an approximation error, which is then related to this expressivity, which we said before. Then you say, okay, but I still don't have the distribution which is in the background. I only have my sample values. So then I make the sample error, which you can view then as also a generalization. So you need to generalize to get to this from the sample values to your true distribution. And then also you have an algorithm which computes your solution. That algorithm will make an error. So this is then the learning or training error, which comes from the optimization. So these errors or these parts which we discussed, what are important concepts or questions in the theory of deep learning, you actually see here, except for the explainability. So that's it. Okay, and so there are a lot of approaches in learning theory. But I think the way people view deep learning is that this is, in some sense, a universal method. This is very vague, but in some sense it performs much better than many of the previous approaches. Okay. Okay. Good. Yeah. So let's. Yeah. Maybe let me see. Okay. Yeah. So let's. Before we make the break, let's look at a bit more sophisticated definition of deep learning, of deep neural networks. So where do they come from? They come from mimicking the human brain. And so how that works is you have these inputs. They are amplified. You sum them up. And then either the neuron fires or not. So you compare this to some B, which is the bias. And so this is, in a way, the basis for what each neuron now in a neural network does. And so an artificial neural network or an artificial neuron is a function of this type. You have the activation here, and you have this sum. Now, if the activation is this Heaviside function, it's exactly what I had from the previous slide. Either it fires or not. But people take a lot of different choices. There's also the sigmoid, rectifiable unit, softmax, and so on. So there's a whole zoo of different activation functions. This, for numerical reasons, is typically considered the best. But also theoretically, it's not clear which of those is maybe better than the others. Good, so then, you have each function in a neuron. You stack them up. You get what's called a feed-forward neural network, so which goes from one side to the other. And let's now be a bit more specific about the definition, because I think in the literature which you observe, this definition is not precise enough. And you will see in a moment why. So what we do here is it's exactly the same definition as we had before. And now we define this to be what we call the architecture. So these are these weight matrices, and these are the biases. And then we define what we call the realization. So we separate the architecture from the realization, from the function. I think it's clear. So these are these weight matrices and biases, and now the function itself, it's exactly the same function we already defined before. Here now defined in an iterative way, so we have x, then we apply the first layer, and so on. Yeah. Good. Why do we separate this? The reason is that different architectures can actually lead to the same realization. And so therefore, if you want to be really precise, and also from an expressivity viewpoint, you need to make this distinction. Good. What are important values here? As we saw, the total number of neurons is important. If you just sum up all neurons present, the number of layers, the number of weights of edges, which is the zero norm of these matrices. Yeah, so remember, these matrices indicated if you have a 0, you don't have an edge. If you have not a 0, it represents an edge. So you need to sum up the number of non-zero entries. And then people are interested in efficiency. So this phi is sparsely connected if the number of connections is small. It's a shallow network if the depth is small, and deep neural network if that is large. And for us, important will be this notation. So a neural network, the input dimension, the number of connections, the number of neurons, and the length of it. And also, at some point, you will be concerned with the overall complexity, and we are not happy with just looking at the connections. We also would like, since you also need to save and store the weights, we also want to bound the weights. Well, and so this will be then our notation, but each time this pops up, I will say again what this means. Good, and so this is one reason why we distinguish this, because the neural network, we can design a neural network which actually does nothing with a ReLU. So if this is my, so B1 and B2 are equal to 0, if this is my A1, this is my A2, then one can just write down that if I now build this, if this is my architecture, then this the realization of it with respect to the ReLU doesn't do anything, it's just the identity. And so therefore, the architectures are different, but the realizations are the same. Okay, and so to be precise, therefore, this distinction is important. Good.
I didn't quite understand. Can you go back to that? So, are you forced at every neuron to apply value? Do you require at every neuron that you apply value? The
so here,
activation
yeah.
in your network. So there are others that are skip channels where you can just push X through. But here you're actually applying value.
That's right. So you're right. I mean, there are also residual neural networks. So where you have a neural network and then you have these skip connections. So in that sense,
you don't have that here.
Yeah, so if you have that, I mean, then certainly also it could happen that, let's say, this X is just pushed through. But here, I mean, the point I just want to make, I mean, this is nothing deep or anything. The only point I want to make here is that you can create neural networks, which are just the identity, and so therefore, you might want to distinguish between the architecture and the function which the neural network represents.
So, I just want to make sure, because this is always a point when I'm reading papers. So if I input a negative number, you will have to, in order that it doesn't get truncated to 0 by value, you will have to add some good number or some number to it. Then you will apply value, and then I guess you'll subtract the number again.
Yeah, but therefore here, so this is set up in such a way that if you put in a negative number, it's actually passed through here. Yeah, so because that becomes positive, and if you apply ReLU, this is actually passed through. So therefore, I mean, this very easy architecture is just the identity. So no matter if you have a negative or positive.
And this is where, so you have to restrict the, if you want a bounded, if you require boundedness, you have to restrict the x's to be in some range. Minus 8 or 8.
You mean for this?
Well, if you would put a big negative number, you're gonna have to add a big.
So this
positive number.
network-
You were concerned in your network about keeping the parameters always bounded, you said.
Oh, yeah. Later on, we want to design networks which are memory efficient. Here, it's just the point that there are, I just want to make a point why I think it's important to distinguish between the function the network gives us and the architecture. And so what I would like to say here is, there are networks which are just the identity, so this distinction becomes important. Okay. Good, so these are the points we will now go through. But I think also, according to my voice, it might be good to make a short break, maybe of, 5 minutes or so. Yeah, maybe we continue at 3 sharp, so then we have 7 minutes to. Okay.
Thank you.